Welcome to your own channel of Right Funda.
Here is another paragraph-based question from electromagnetic induction. Let's read the question. There's a passage, first we'll be reading and we'll be giving the answer to this question. Let's read it. A conducting rod OD of mass m and length L rotate about one end O. So here is the rod there, OD, and it rotates about this end like this. Its other end sliding slowly on a circular conducting ring as shown in the figure. This rod will be sliding over there. A constant and uniform magnetic field B acts into the plane of the ring, and a force having a constant magnitude capital F acts on the rod at the end D. At this point there is a force there along the tangent to the ring. Assume that the space is gravity free and there is electrical contact between the rings and the rod at D. The ring and the rod have negligible resistance. There is a small gap in the ring between P and the Q so that the current flows along a unique path. Okay. And the question is asking that find the angular acceleration in the rod. And second question is saying the induced EMF in the rod as a function of time. Two questions has been asked. So what is given that this is a rod and this is, we are applying some force on this, so it can freely rotate about this point, and there is a presence of uniform magnetic field there, and also there is a capacitor C is connected here, you see, and there is a gap in there. Okay, and there is a perfectly conducting ring there. There is a perfectly conducting ring there. So as you apply the force F to this, with what angular acceleration the rod will rotate, and what is the induced EMF between the ends of the rod. So now you have understood the question. You may pause the video and you try solving the problem. After that, again, you can resume the video and you can see the solutions. Now I'll be discussing the solution here. Okay. Let's see, we have to find the angular acceleration of the rod. Why the angular? Because this force is there, the force will be producing some torque and there should be some angular acceleration. But the torque not only depend upon this force, if there are any other forces also acting on this, it will depend upon that thing also too. So as this force is there and the rod starts rotating here, there will be a motional EMF across the rod. There will be a motional EMF, this will behave like a cell. And because of this cell, if any closed path is there or some path available to this, then current will start flowing. Current will start flowing through this. So if the current will flow through the rod, then what will happen? There will be force. Current carrying rod placed in a magnetic field experiencing force. There will be force will be there, and that force too will produce the torque. So not only this force will produce torque, that force, this external force F, as well as the magnetic force, both will be producing torque. So we need to calculate the magnetic force, and to know the magnetic force, we require the current flowing through the rod. And to know the current flowing through the rod, we need to apply Kirchhoff's law in the circuit, and we need to know the EMF induced in the rod. And EMF induced in the rod depends upon the angular speed it is moving, because in this rod here to here, how much EMF is there. We have solved similar problem. Then whenever a rod moves in a circular path with a angular speed omega, every element there will be induced EMF will be there. And if you integrate the induced EMF, the formula for induced EMF is equal to B dot dl cross V. This is that if you integrate this, then we get the induced EMF between the O point and D point. We can find the induced EMF. And let's start solving the problem, and we'll be discussing gradually. So what will be the induced EMF? We know that if the rod is rotated, the induced EMF across the ends of the rod equal to half B omega L square. Half B omega L square. But in this, once you integrate this one, you'll be getting between this, and there will be at the positive. It will be rotating like this. This will be positive. This will be negative. Okay. Higher potential will be O and lower potential will be equal to D, because it is rotating anti-clockwise we have taken. So as there are induced EMF there, then, and this is a perfectly conducting rod is here. This is a perfectly conducting rod. But as if a current, which path the current will go? Suppose this is behaving like a cell of this half B omega L square. There is the EMF is there, and due to this EMF, current will start flowing. But current cannot go through this way because it is disconnected here. It is disconnected here. So current has the only path to go like this. But again, capacitor through it cannot go. But capacitor can accumulate charge. So if we apply the Kirchhoff's law in this loop, then we can write the equations that plus E, the induced EMF, and applying Kirchhoff's law, we can get the Q by C minus E induced EMF equal to 0, or the charge that will be accumulated there depends upon the instantaneous EMF across the rod. Why I'm saying instantaneous? Because they are depending upon the omega of the rod, this EMF of this will be keep on changing. So whenever the omega is there, at that instant, how much charge must be accumulated there in the capacitor to obey the Kirchhoff's law is equal to Q is equal to C into E. Q is equal to C to E, we got one relation. And E value we know is equal to B omega L square by 2. So if you substitute the value, so then we can get a charge as a function of omega. Q is equal to C times the V omega L square by 2. We have substituted. Once you get the charge on the plate of the capacitor, then and there is no resistance anywhere there, so we can find out by differentiating rate at which the charge is getting accumulated. So we can differentiate the charge and we can get the current that will be flowing in the rod or to the plates of the capacitor. dq by dt I differentiated, and dq by dt is the Q, where Q is the charge on this plate of the capacitor. Q and minus Q charge will be separated. This Q we have calculated like this, and this dq by dt we have taken the current, and the current flowing to the rod can be written as I is equal to CB L square by 2, and this d omega by dt, the rate of change of angular velocity, is nothing but the alpha. So I is equal to CB L square by 2 into angular acceleration of the rod, and we got the current as a function of angular acceleration. So we got this relation. After that, once you get the current, then we'll be seeing the how much torque will be acting on the system, on the rod. So to calculate the torque, so let's consider a small element at a distance x and length dx, because the force is not acting at one point, force is acting everywhere. So in this, suppose that small force that is equal to df. So whatever we are trying to rotate in anti-clockwise sense, because but this magnetic force is trying to rotate in the clockwise sense. This will be producing torque about this point in the clockwise sense. That should happen according to Lenz's law. That should happen. We try to rotate like this. That should be another torque to oppose the cause producing it. This force is here, and let's calculate this force and calculate the torque about this point. So how much force will be acting? That we know the df is equal to I into dx cross b. I into dx cross b, and the force will be, we can calculate this force is equal to I, we have taken here equal to CB L square by 2 into alpha. We substituted this value, I value we substituted here, and dx into v is the force that will be perpendicular to the rod. So this small force will be producing torque, and the torque due to this small force will be equal to R cross F. I will take the R cross F, this perpendicular to x cross dfm, the small force, the magnetic force I have done a dfm, the minus k cap means in the clockwise sense will be there. So this I will substitute df value, the value of df that we have got, that we substitute here, substitute the value, and we got the small torque due to as a function of x. And if we integrate this one, we can get the total torque acting on the rod that can be calculated. And this x is my variable, and x varies from 0 to L. X varies from 0 to L. Then we can calculate total torque that will be acting will be CB square L square by 2 alpha into L square by 2. This much anti-clockwise torque, clockwise torque is acting due to magnetic force. Due to the magnetic force, this much torque is acting here. So we got one result. Let's mark this. After that, in addition to this, there will be another torque also to be here. That another torque is the force that will be applying, that will produce a torque like this, but that force will be producing a anti-clockwise torque will be there. This magnetic force is producing clockwise torque, and this will be producing the anti-clockwise torque. This point of application is distance L from this. LF is the torque in the k-cap direction. So two results we obtain. One is the magnetic force that is producing torque, and another is the force torque produced by the applied force F on this. The net torque that we want to calculate, net torque acting on the rod is equal to tau net is equal to tau magnetic plus tau F. And we put those values at this much in the k-cap direction, net torque is acting. Okay, and net torque will be equal to I into alpha, because rotating about that axis, I has to be taken about the rotation axis. So ml square by 3 into alpha is equal to this much. So if I arrange this term, here also alpha is there, here also alpha is there. If I arrange this, I'll take to this side, then I can calculate the alpha, or the angular acceleration of the rod can be calculated. I've taken to that side, and alpha is, I arrange this one, LCM I've taken, and alpha is coming out to be equal to 12 L by 3 ml plus 3 b square L cube. That 1 L get cancelled here, 1 L get cancelled. So this is the result we obtain, angular acceleration with which the rod will be rotating. And you see this alpha came out to be a constant quantity. Alpha is a constant, it does not depend upon it. So we have seen that force will be acting, we are rotating like this, and the magnetic force will be acting, and finally we found out the alpha to be equal to this much, and we have taken the this much, kept it. Okay. So once you got the alpha, that's, let's see, check the Excel, 12 by 4 ml plus 3 b square L cube. 12 L plus 3 ml plus this. So A option is correct. Okay. Next question is saying that find the induced EMF in the rod as a function of time. What is the induced EMF? We have checked the induced EMF is equal to this much. Once you know the omega at any time, omega, that depends on the omega at any time, and we find out the alpha, and alpha is a constant quantity. So once your alpha is there, then omega will be equal to alpha into t. Right, alpha is constant. So from this alpha, we can easily calculate the omega as a function of time, and that in this omega value will substitute here, then we get the answers for this, and that substitute omega is equal to alpha t. We substituted alpha value, we substitute from the above equation that we calculated, this alpha we substituted, and we obtain finally the induced EMF in the rod will be equal to 6b L ft by 4m plus 3 b square L square. This is the final result we obtained for the induced EMF that will be as a function of time. As time increases, the induced EMF will be increasing. This is a linear function of the time induced EMF is, and we have checked that in this case, this end will be positive. This our center point will be positive, and the periphery point will be negative. There is a higher potential as compared to lower potential, and how much value that will be there is equal to 6b LFT by 4m plus 3 b square L square. Let's check the answer. Equal to 4 6b LFT into is equal to C, my correct answer. A and C the correct. So we have seen that if we apply the force here, this will be rotating, and induced EMF try to opposite torque to this torque, and eventually it will be rotating with a constant angular acceleration, and omega will be keep on increasing, and that's why induced EMF is a function of time. Linearly induced EMF will be continuously changing, and the capacitor will be getting charged continuously. Okay, hope you have enjoyed the solutions, and if you enjoyed the solution, like this video, share the video with others, and we'll be coming with another interesting question in the next video. Till then, bye.